present MultiModN, and on behalf of a great team of collaborators, both from our local EPFL and from the Yale School of Medicine. We have some familiar faces up there. I think you recognize Martin from the keynotes, and Annie, who will be giving a keynote later today, so you guys should all attend those. But we're excited to have a very diverse team and a cross-lab collaboration for this work that we're bringing you. So, what's the problem? As Alan even mentioned in his introduction, multimodal models are becoming very, very popular these days, from Google's Gemini to GPT-4 and various other domain-specific multimodal models. We've seen that these kind of tasks are more important, and the data that we are collecting in these kind of different modalities are also more prevalent and pervasive. And we can leverage the synergistic predictive potential of a lot of these different modalities together to create these multimodal models that might be better than models that use any modality individually. These models have to deal with inputs of drastically varying sizes, including images, text, sound, etc. Now, current approaches to multimodality fuse these representations in parallel. They take images, audio, video, and fuse them all to the same shared embedding space to leverage those connections between those modalities. However, we argue that this approach actually limits interpretability because you can't disambiguate which modality caused what part of the prediction, and creates a dependency on modality availability. When there is missing modalities, this architecture kind of starts to fall apart or be biased in terms of what representations it has. So, our research question is, can we address these limitations of the current multimodal architectures with sequential fusion instead of parallel fusion? And throughout the rest of this talk, I will aim to convince you of 5 things. The first is that MultiModN matches parallel fusion, which is the traditional way of doing multimodal models, for a range of real-world tasks. That the new architecture that we present is composable at inference. That importantly, it is actually the first approach that is inherently robust to the bias of missing not at random modalities, or MNARM modalities. And it is inherently interpretable, which is of particular interest to this track. And also it is easily extended to any number and combination of tasks. So, this looks like a large diagram, but I'll walk you through it bit by bit. On the right, you'll have P-fusion, which is kind of our traditional way of doing multimodal models. What you see is that images, text, time series, etc., are each passed through separate encoders, which are then concatenated in, or averaged, etc., into some kind of shared embedding space, which are then decoded on any downstream tasks. The architecture we propose is on the left, MultiModN. And what we see is, for example, for a specific modality that is passed in, for example, images, it gets passed to an encoder, but kind of like an RNN, there's a notion of autoregressive state, where there is a general representation of a patient, a student, a user, decoded on any number of tasks. This can be regression tasks, it can be classification tasks, etc. And through this architecture, the state is then updated to then decode on those tasks again. And in this way, the modalities are kind of separated from each other, but are still shared in this latent space to leverage their predictive potential together. For a very concrete example, let's take a student in an online course. S0, all the way over there in the corner, kind of represents the average notion of a student. And this student we can predict to be performant in their next week, or to drop out at the end of the course, or to have pass-fail prediction. Then let's say the student watches a video. That video information is passed through an encoder to then update their state alongside their previous state. So now this student is represented through this state vector to have some notion of knowledge, which is then decoded at any point in time. And then let's say they answer a lot of quiz problems. That is passed through a different encoder for quizzes, and that is then used to update their state and decode it on any number of tasks. Now, there are some advantages here in this architecture that are particularly notable. One, missing modalities are not represented at all in this architecture. So when we don't have data, it's not encoded in the input space in the same way that pFusion requires a limited and already predefined size of input as per E2 on the screen. And the second is that because we have all of these modular encoders and decoders, we can easily integrate a new encoder or decoder into this architecture. So how did we evaluate this model? We look at 10 real-world tasks across healthcare using the MIMIC datasets with both the chest X-rays as well. Education, in fact, using MOOCs here at EPFL to do the evaluation, and weather forecasting with the multimodal weather 2K benchmarks. And as you can all imagine, if you're working with multimodal data, these data sets are quite hard to both obtain and identify. So in these cases, we are using 921 patients from tertiary care in a Boston hospital for our healthcare case, 5,605, about 5,000 students in a MOOC, which has over 1 million interactions if you're counting every video interaction or problem interaction that the students solve, and 1,866 ground weather stations covering a large range of area. So these are really diverse, real-world, pretty hard tasks with very different ranges of multimodal data. And specifically, if we're looking at the types of data in these situations, for MIMIC, we have both the demographic data, which is tabular, chart events, which is time series, chest X-rays, which are images, echocardiogram notes, which is text. We have problems and videos in the education setting. And for the weather forecasting setting, we have geographic information, air, wind, land, and rain hourly measurements, which are both time series and tabular. And for our prediction tasks, we evaluate both on regression and on binary classification, but both continuously and statically in time. So either one prediction at the end or temporal predictions throughout. And what we find, addressing that first point, is that MultiModN, which is the colored lines on each of these graphics, is performant on individual tasks. It at least has overlapping confidence intervals with 10 tasks across healthcare, education, and weather. We also found that MultiModN is naturally extensible to the prediction of multiple tasks without harming the performance of single tasks. So when you include multiple of these decoders together, the performance of single decoders don't get harmed. And what you see here with the error bars is that each confidence interval overlaps. So you can consider that the performance is about the same or statistically significantly together. And our model is interpretable by design. So we produce two different kinds of interpretability here. The first is global interpretability, where you can identify how much each modality contributed to the prediction. So what you see in the top image is for two tasks, ECM prediction and CM prediction, which are two different diagnoses. We see that the text modality actually made the most difference in the predictions every time. With parallel fusion, we cannot clearly identify how much each modality contributes to the prediction. At the bottom, you see a local interpretability technique. What you can identify with this is what modality caused the decision to flip. And before even looking at, for example, the state vectors or what the encoders have or any of these traditional notions of interpretability we saw in the previous talks, even by just looking at the output and disambiguating how exactly each of these modalities are combined together, we can identify that for these two individuals, that the image data was the one that caused their decision to be negative for the diagnosis. Now for the education case, we have 3 tasks, including next week prediction, dropout, and general pass-fail prediction. And although both problem and video interactions are important for both, we see that for task 4, which is dropout predictions, problem interactions were more important than video interactions. And specifically, what we see that's quite nice in the education scenario is when parallel fusion gets it wrong, it's not easy to identify why. In these 2 cases, these were 2 students that were that were actually going to fail the course, but were predicted to pass. And what we see is in task 3 and 4, we can clearly see whether the problem data or the demographic or kind of their prior information and their prior workload or their video interactions caused the change in prediction. Versus here, we are not able to disambiguate that, and that is a key problem with current multimodal architectures. Notably, MultiModN is robust to bias from missing input modalities. So if you take a look at the graphic, what you see is when we have some kind of modality missing in the train set and a different kind of modality missing in the test set, our model is fairly resistant to this problem. Of course, there is still some minor drop in performance because there is some missing data, but parallel fusion models exhibit catastrophic forgetting. And why this is important is because of low resource settings. So if you take an example for low resource settings in healthcare, where a lot of the models that we use in healthcare, especially multimodal models, are trained in high resource environments. So for example, they might include MRI scans. But then if you move to a low resource setting and they don't have that data, that missingness in pattern, even if they are masked, is encoded in the embedding space. It's a situation that the model was never trained for, and that distributional shift is quite large. But what we see with MultiModN is that it's actually robust to this difference. And so we're really excited to state that there are some new experiments with MultiModN that are going into the real world in clinical trials. So we have Annie in the back if she wants to raise her hand. She is a wonderful author on this work who is deploying some clinical studies for MultiModN for both pneumonia and tuberculosis diagnosis in low resource settings. And she's leading an amazing effort to train more than 100 doctors to collect this multimodal data and recruiting thousands of patients across South Africa, Tanzania, Namibia, and Benin to enact these clinical studies in these low resource settings. And we're seeing that MultiModN, by design, is robust to this missing data and is interpretable, and so is better to use in these applied scenarios. There's a recent EPFL article about it if you want to learn more. So, overall, I've hopefully shown you that MultiModN matches performance to parallel fusion for a range of real-world tasks and is flexible and composable at inference, and it is easily extended to any number or combination of tasks with new encoders. We've also shown that the model is inherently interpretable in both the healthcare and education settings with examples, and that is robust to the bias of missing modalities. We've also, with our team, included a very nice repo with a very, very general solution for MultiModN. So we'd encourage you all to try our architecture, and thank you all for your time.
Okay, questions? At least one? Oh, you got there. Thanks.
Hi, a really nice talk, really enjoyed it. My question is that, is it possible to get a more microscopic view into like which component of an embedding causes like a more of a like a local explanation? Right now it just says like, okay, text is like most impactful, right? Like which components of the text were impactful towards that certain prediction?
Right, that's a great question. So at this level, the problem that we were trying to address was disambiguating modality predictions. But of course, there are lots of different explainability techniques that we've even heard about today that can be applied on top of LLMs, or even just a simple attention layer to see what part of the text is relevant into the prediction. And this model doesn't prevent any of that from happening. You can always apply a traditional explainer on top of any of these different encoders or decoders to get additional explainability. But the interpretability by design, I think, is key, because if we start designing these models to be robust and interpretable in the way they're actually useful, people don't have to go afterwards and put an explainer on top. So perhaps including attention layers in encoders would be a very valid way to use this model as well.
Okay, how do I get there now? Can you just scream, and in Italian I will scream back?
Thanks so much, very interesting. Did you explore the ordering of the fusion? How does it impact the outcome?
Yeah, this is a great question and one we get often, and I probably should have included it in the presentation. It's been shown that for example, a set of modalities that are included, let's say, in one time step, let's say you have text, tabular, time series, etc., it is order invariant. So from the time you have the initial state to the final prediction, the prediction will remain the same, no matter what ordering that you put. However, for interpretability, it is important that the marginal contribution of each encoder will change depending on the order that you put it in. So the architecture itself, performance-wise, is order invariant. But in terms of interpretability, if you're looking from a global perspective of not this specific ordering, but any ordering, you would have to run that experiment to find which modality is most useful.
Okay, let's thank the speaker again.